Before starting the class of composition of functions, let us discuss about identity function and equality of functions first. What is meant by identity function? Identity function, from the word itself you can understand the meaning of it. Identity function, it's a function which doesn't affect the identity of an element in the domain. Usually, I is the letter which is used to denote identity function. And how can it be defined? I of x equal to x itself, for all x belongs to the domain in which this function is defined. It can be defined in any set. For example, let capital A equal to set small a, small b, small c. And IA, this is the identity function defined in the set capital A. And how can it be defined? IA of small a equal to small a itself, IA of small b equal to small b itself, IA of small c equal to small c itself. That means each element in the domain is associated to itself. It does not change the identity of the element. This is identity function. And what is meant by equality of functions? Two functions f and g are defined in the domain capital D. And what can be the meaning of equality of functions? The meaning is just agreeing with our expectation. That means two functions are said to be equal if their effects are the same on each element in the domain. How can it be defined? F of x equal to g of x for all x belongs to the domain capital D. Then f and g are said to be equal when two functions f and g are defined in the set capital D, which is the domain of both functions, and f of x equal to g of x. That means image of each element under f and g are the same. In this case, we call these two functions as equal. Now let us discuss about the composition of functions f and g. Consider the functions f and g defined as in the figure. That is, f is a function from a to b, g is a function from b to c as explained in the figure. Now you go through the figure, you may get a connection from 1 to minus 1 through this a. That is, there is a path from 1 to a and then from a to minus 1. There is a path or connection from 2 to c and c to minus 1, 3 to d and d to minus 2, 4 to d and d to minus 2. That means there is a association from 1 to minus 1, 2 to minus 1, 3 to minus 2, 4 to minus 2. That means each element of capital A is associated to a unique element of capital C in a particular manner. How is this possible? That means to get this connection from 1 to minus 1, we want to apply G on the image of 1 by f. That means G of f of 1. What is G of f of 1? It is equal to G of A equal to minus 1. That means by joining f and g in a particular manner, you may get an association from 1 to minus 1. The element 1 from capital A to the unique element minus 1 of C. How is this possible? The function g is to be applied on the image of 1 by f. How is it denoted? G dot f of 1 equal to minus 1. Similarly, what is g dot f of 2? It is also minus 1. G dot f of 3, it is minus 2. G dot f of 4 equal to minus 2. That is, this joining of f and g in this way is the composition of f and g. How can it be defined then? How can it be defined? Let small f, it is a function from a to b. Small g, it's a function from b to c. Then g dot f is a function from A to C. And how can it be written? G dot f of x equal to G of f of x. That means the image of x in a particular domain by G dot f is the image of G on the image of x by f. Here, can you find out f dot g? That means, can you find out f of g of a? What is g of a? G of a is minus 1. Can you find out f of minus 1? It is not possible because the domain of f is capital A and g of a is an element of C, not A. Therefore, here f dot g is not possible. Therefore, what is the condition for the existence of the composition of function g dot f? That means the range of f should be a subset of the domain of G. Only then G dot f is meaningful. Now, let us take the case of real valued functions. Consider two real valued functions f and g. What about the domain and range of real valued functions? They are either a set of real numbers or part of set of real numbers. In this case, since both are set of real numbers, g dot f and f dot g may be meaningful. Consider this example where f of x equal to x plus 1 and g of x equal to 2x. What about the range of small f? Range of f of x is the set of real numbers and the domain of g is also the set of real numbers. Therefore, g dot f of x is meaningful. And how can it be? G dot f of x equal to g of f of x equal to g of x plus 1 equal to 2 into x plus 1. That means g of x equal to 2x. Therefore, g of x plus 1. How will you get it? In the place of x, you have 2. Write x plus 1. 2 into x plus 1 equal to 2x plus 2. Can you find out f dot g? What about this? The range of g, which is the set of real numbers, is the same as the domain of f. And so, f dot g is also meaningful. What is f dot g of x? Equal to f of g of x equal to f of 2x. What is f of x? It is x plus 1. f of 2x is 2x plus 1. You see this? G dot f of x is 2x plus 2 and f dot g of x is equal to 2x plus 1. Both are unequal. F dot g is not equal to g dot f. Now, this is the case where both g dot f and f dot g are meaningful. Now, you consider this problem f of x equal to 2x and g of x equal to 1 by x. Is g dot f of x is meaningful? What is the range of 2x? Range of f of x, it is a set of real numbers, but the domain of g is the set of real numbers minus singleton set 0. That means the range of f is not a subset of the domain of g. Therefore, in this case, g dot f of x is meaningless. What is the reason? What is g dot f of x? It is g of f of x. Here, what is g of f of 0? Can you find out this? What is f of 0? It is meaningful. It is 2 into 0, 0. But what about g of 0? G of 0 is... Can you find out g of 0? No. G is defined in the domain set of real numbers minus singleton set 0. Therefore, g dot f of 0 is not defined. But it can be defined. G dot f of x equal to g of f of x equal to g of 2x equal to 1 by 2x provided x not equal to 0. That means by restricting the domain of f as the set of real numbers minus singleton set 0, g dot f is also meaningful. Now let me give an example. It is an interesting example. That means to define or to explain this composition. Suppose I have rupees X with me, rupees X, and there is a magic box which has two compartments, in which the first compartment has a capacity that if you put or if you keep X rupees in this box, when it comes out to the second compartment, 500 rupees can be added to it, and the amount in the second moved to the second compartment is 500 plus X. And the second compartment has a tendency or capacity to make it double. That means when it comes out, it is double. That means it becomes 2 into 500 plus X. That means if I put 100 rupees in the first compartment, when it is moved to the second compartment, it becomes 500 plus 100, that means 600. Where it get multiplied by 2, that means when it is taken outside, it becomes what? 2 into 600. In the first compartment, it becomes 500 plus 100, that is 600. It is moved to the second part, where it get doubled, that means it becomes 2 into 600 equal to 1200. That means here you know f of x equal to 500 plus x and g of x equal to 2x. And what is g dot f of x? G dot f of x is equal to what is g of f of x equal to 2 into 500 plus 6. This is the composition. That means if I put X rupees in the first compartment, when it is moved to the second part, it becomes 500 plus 100, that is 600. Where it get doubled. Therefore, when it is taken outside the box, it becomes 2 into 600, that means 1200. This is the composition. This is a tricky example of composition of two functions. Now, let us discuss some properties of composition of functions, in which the first property is if f and g are 1-1 functions, then g dot f is also 1-1. Let us prove it. Consider the function f from a to b and the function g from b to c, then definitely we know g dot f is their composition, it's a function from a to c. In order to prove that g dot f is a 1-1 function from a to z, you take two elements x1 and x2 belonging to capital A and consider g dot f of x1 equal to g dot f of x2. Then what happens? If g dot f of x1 equal to g dot f of x2, the meaning is g of f of x1 equal to g of f of x2. Since g is a 1-1 function, what can you write it? That is f of x1 equal to f of x2. And here f is also a 1-1 function, and so from this equation f of x1 equal to f of x2, we can write x1 equal to x2. Therefore, what did you get here? If g dot f of x1 equal to g dot f of x2, x1 equal to x2, which means g dot f is also a 1-1 function. Now, you know, if if any of the function f or g is not 1-1, then g dot f is also not 1-1. Now, let us take the second property. The second property is this. If f and g are onto functions, g dot f is also on 2. Let us prove this. Consider f from a to b and g from b to c. Then what about g dot f? G dot f is a function from a to c. In order to prove that g dot f is a onto function, you take a small c belonging to capital C, which is the codomain of g dot f. Now, since g is onto, what can you write? Corresponding to this c belonging to capital C, there exists a small b belonging to capital B, such that g of b equal to small c. That means corresponding to this small c belonging to capital C, we got a small b belonging to capital B, such that g of b equal to c. Now, f is on 2. Therefore, what can you write? Therefore, corresponding to this b belonging to capital B, what can you write? There exists a small a belonging to capital A, such that what? F of A equal to B. That is what? Corresponding to this C belonging to capital Z, we got a B, and corresponding to this B belonging to capital V, got an A. So that what happens? G dot F of A equal to G of F of A equal to G of B equal to small c. Corresponding to the small c belonging to capital Z, we got a small a belonging to capital A, such that G dot F of A equal to C, which means G dot F is on 2. As in the case of 1-1 functions, if either of the functions is not onto, G dot F is also not onto unless C is a singleton set. If C is a singleton set, that means this is capital A, this is capital B, and this is capital C. This contains small a, small b, small c, 1, 2, 3, 4. F is a function from A to B, G is a function from B to C, A is mapped to 1, B is mapped to 1, C is mapped to 2. Suppose capital C is a singleton set which contains only one element. Let it be that element B minus 6. And all the elements of capital B are associated to this single element 4 by this function G. In this case, G dot F is onto. No problem. Third property is composition of functions is associative. Composition of functions is associative. Yes, what is the meaning of associativity of the composition? Let us consider this function f from A to B and G from B to C and H from C to D. Then H dot G dot F equal to H dot G dot F. This is the meaning of associativity of composition of functions. Let us prove this. If G is a function from B to C and F is a function from A to B, then what about G dot F? G dot F is a function from A to C. G dot F is a function from A to C and H is a function from C to D. Then what about H dot G dot F? This is the composition of H and G dot F. This is a function from A to D. Similarly, now let us take this. What about F? f is a function from a to b, and h dot g, it is a function from b to d. Then what about h dot g dot f? This is the composition of h dot g and f. This is a function from a to d. Therefore, both h dot g dot f and h dot g dot f both are functions from a to d. Now, let us consult or let us discuss their effects. How will you take, let small a belonging to capital A, then h dot g dot f of A equal to, what is this? H of g dot f of A equal to h of g of f of A equal to, how will you write? H dot g of f of A equal to h dot g dot f of A. Therefore, what can you write? H dot g dot f. That means the effect of h dot g dot f on A equal to the effect of h dot g dot f on A. That means you can write h dot g dot f equal to h dot g dot f. Therefore, the composition of functions is the property, fourth property, the composition of any function with identity function is the function itself. What is it? Let small f, it's a function from a to b, and ia and ib be the identity functions in capital A and capital B. What does it mean? Ia of a equal to a for all small a belonging to capital A, ib of small b belonging equal to small b itself for all b belonging to capital B. We need to prove that f dot ia equal to f and ib dot f equal to f. How can you prove it? Take a small a belonging to capital A. F is a function from a to b, and so f of, let b be the element in capital B as the image of small a. That means f of a equal to small b. Then what is f dot ia of a? F dot ia of a equal to f of ia of a equal to f of a. That's enough. No need to write b. That is image of f dot ia on a equal to the image of a by f itself. What is the meaning? F dot ia equal to f. Similarly, what is ib dot f of a? This is equal to ib of f of a equal to ib of b equal to b equal to f of a. Therefore, the effect of or image of a by I dot b dot f equal to the image of a by f, which means ib dot f equal to f itself. Yes, next property, the composition of, fifth property, the composition of an invertible function f with its inverse is identity function. Identity function is, what is the meaning? Let small f is an invertible function from a to b. Then what is f inverse? F inverse is a function from b to a, and remember, f inverse is the inverse of f. We need to prove that f dot f inverse. What is f dot f inverse? It's a function from b to b. We claim that f dot f inverse equal to ib and f inverse dot f equal to ia. Yes. Let small a belonging to capital A and small f of A equal to B belonging to capital B. And what is f inverse B? F inverse B equal to small a, because f inverse is the inverse of function f. Now, what is f dot f inverse of B? Equal to f of f inverse B equal to f of A equal to B equal to IB of B. Therefore, what can you write? F dot F inverse equal to IB. And what is F inverse dot F of A? Equal to F inverse of F of A equal to F inverse of B equal to A equal to IA of A. What can you write? F inverse dot F equal to IA. In this video, we have seen the composition of two functions and its properties. In my next video, later we can discuss about the algebra of functions. That is the addition, subtraction, multiplication and division of functions, and also some graphs of functions. Okay.